something impossible happened at perihelion between October 29th and 30th. As 3IATLAS slipped behind the sun, vanishing from our view, spacecraft instruments detected something no one expected. It turned bluer than the sun itself, not just a subtle hue shift, bluer than a 5,800-degree star. Then, it accelerated, violently, 135 kilometers per day squared, with no visible source of thrust. During that same time, NASA went silent, tangled in a government shutdown, and the images from Mars, the ones that could have explained everything, disappeared into bureaucratic darkness. Astrophysicist Avi Bay ran the numbers. If this phenomenon is natural, we should witness a massive gas cloud by December, the result of 10% of the comet's mass being ejected into space. But if that cloud never appears, then we're staring at something that doesn't fit any model we've ever built. 9 documented anomalies, 9 unexplained behaviors in a single object. And now, the scientific community is arguing whether we should even be asking if this thing is a comet at all. On December 19th, 3IATLAS will make its closest approach to Earth. That's when every major telescope on the planet will turn toward this mysterious traveler. And, for the first time, we might finally discover what we're really looking at. Right now, the data we already have is breaking the rules of physics. If confirmed, it could become the most significant astronomical anomaly of the decade. But before the hype, let's understand why this matters. The impossible blue shift, that sudden change in color, is not just a visual oddity. In astronomy, color is data. Every wavelength tells a story of chemistry, temperature, and energy. A red comet reveals dust scattering sunlight, or carbon compounds absorbing some wavelengths and reflecting others. A green comet points to diatomic carbon, molecules excited by ultraviolet light, glowing with that familiar emerald hue seen in many comets across the solar system. But blue? That's different. A true blue emission suggests energies far beyond normal cometary activity, temperatures and reactions that should not occur in such an object. If the spectrum is accurate, then either our instruments are lying, or 3IATLAS is not behaving like any comet we know. This is not just another entry in the cosmic catalog. It's a challenge to our understanding of how matter and radiation interact in deep space. But blue means something else entirely. Blue isn't just reflection, it's emission. It means that something inside or surrounding 3IATLAS is generating its own light. Light in wavelengths that should never dominate the spectrum of a frozen, icy body merely warmed by a distant star. Astrophysicist Alo put it bluntly: dust is supposed to scatter sunlight, not create it. The surface of 3IATLAS should be roughly 20 times colder than the sun's photosphere, which by all known physics would make it appear redder, not bluer. For it to shine bluer than the sun itself violates basic thermodynamics. It breaks our understanding of how cold matter interacts with stellar radiation, and the color history of this object only deepens the mystery. Just a few months ago, in July and August, 3IATLAS glowed a deep red, exactly what astronomers expect from a dusty, carbon-rich body heated by sunlight. Then came September, during the total lunar eclipse. Amateur astrophotographers Michael Jagger and Gerald Riemann, observing from Namibia, captured breathtaking images that showed the comet shifting green-blue-green, a signature of diatomic carbon emission, the same phenomenon that gives many comets their familiar emerald glow. But now, it's blue. Intensely, impossibly blue, a color that shouldn't exist on an object like this, a color that may be trying to tell us something fundamental about the universe itself. The implications of that color shift are keeping some of the brightest minds in astronomy awake at night. Let's unpack why this matters. Why this isn't just another curious entry in the endless catalog of cosmic oddities. When we see color in space, we are witnessing the language of the universe. Every hue is a message written in chemistry and physics, a reflection of the fundamental processes that dictate how matter interacts with energy. A red comet tells us about dust scattering sunlight, about carbon compounds absorbing certain wavelengths and reflecting others. A green comet reveals diatomic carbon molecules, energized by ultraviolet radiation and fluorescing in that familiar emerald glow, a hue we've seen countless times among comets in our solar system. But blue. Blue means something else entirely. Blue means emission, not reflection. It means that something within or surrounding 3IATLAS is generating light. light at wavelengths that should never dominate the spectrum of a frozen, icy body merely warmed by a distant star. Astrophysicist Lowe put it bluntly, dust is expected to rescatter sunlight, not emit it. The surface of 3IATLAS should be roughly 20 times colder than the sun's photosphere, which means it ought to appear redder, not bluer. For this object to shine bluer than the sun itself defies the basic thermodynamics of how cold matter interacts with stellar radiation. This isn't just strange, it's impossible, at least by the rules we thought the universe played by. For 3IATLAS to appear bluer than the sun defies the most basic laws of thermodynamics, the very principles that govern how cold bodies interact with stellar radiation, and yet, the data is undeniable. It comes from multiple independent sources, making it impossible to dismiss as an instrument glitch or observational error. The Stereo A spacecraft, both its HI-1 and Core 2 cameras, recorded the same inexplicable blue shift. Then SOHO's LASCO C3 coronagraph confirmed it. Even GOES-19, a weather satellite that just happened to be monitoring solar activity during the critical window when 3IATLAS slipped behind the sun, captured that same impossible azure glow. These are different instruments, built by different teams, operated by different space agencies, and processed through entirely separate data pipelines. And yet, they all saw the same thing. And what they saw wasn't reflected sunlight. It was emission. That's the crucial difference. The line between a mere curiosity and a true cosmic mystery. When sunlight hits dust or ice, it bounces, it scatters, it reflects. The color we see is simply the light that survives that interaction, the wavelengths not absorbed by the material. But emission is different. Emission means something is glowing. Something within or around 3IATLAS is releasing energy. Energy powerful enough to forge photons of its own. And that changes everything, something inside or around. 3IATLAS is hot enough, energetic enough, or perhaps strange enough to produce blue light so intense it overwhelms the sunlight that should be reflecting off its surface. The obvious explanation, the one every astronomer reaches for first, is gas, specifically ionized gas. Here's how that works. When molecules in a comet's coma, the halo of vaporized material surrounding its nucleus, are struck by solar ultraviolet radiation, their electrons jump to higher energy states. As they fall back down, they release photons, tiny packets of light. Different molecules release different colors. Under the right conditions, carbon compounds can indeed glow blue. So maybe, just maybe, 3IATLAS contains an unusually high concentration of volatile carbon species, creating this vivid blue emission through straightforward photochemistry. But here's the problem. The spectroscopic data we already have, the chemical fingerprints from its earlier observations, don't support that idea. Remember the KEK telescope readings from August 24th, or the Very Large Telescope data from August 25th? They both revealed something peculiar. 3IATLAS has an unusually low abundance of carbon chain molecules, specifically C2, the molecule responsible for the green glow seen in most comets. In other words, the very compounds that should be creating this blue emission aren't there. The C3 molecules, which normally contribute to a comet's overall color signature, are also nearly absent. In fact, the ratio of cyanogen, CN, to carbon chain compounds in 3IATLAS is one of the highest ever recorded in any comet. As Luis Salazar Manzano from the University of Michigan stated in his paper, 3IATLAS is among the most carbon chain depleted comets known. So if it lacks the very molecules that typically produce colorful emissions, what then is making it glow blue? This is where speculation begins, where the line between orthodox science and uncomfortable possibility starts to blur. Some researchers suggest that the blue emission might come from carbon monoxide, CO, molecules being ionized at extraordinary rates, producing a form of blue fluorescence never before observed at such intensity. Others point to the comet's bizarre nickel signature, that persistent emission of nickel without iron, one of 3IATLAS's strangest anomalies. Could nickel compounds, energized by solar radiation, be part of the puzzle? We know that nickel tetracarbonyl breaks apart under ultraviolet light, releasing both nickel atoms and carbon monoxide. Could some exotic chemistry, driven by these breakdown products, be responsible for the mysterious blue glow? But of course, Lowe, predictably, goes further. In his analysis of the perihelion data, Lowe raised a possibility that most of his colleagues would rather leave unspoken. What if the blue color isn't about chemistry at all? What if it's about heat? Not the passive warmth of sunlight on ice, but active heat, internal heat, originating from a source that is not the sun. Lowe noted that for 3IATLAS to appear bluer than the sun, something about it must either be hotter than the sun's photosphere in its emission spectrum, or emitting through a mechanism that preferentially generates blue light. The suggestion, never written outright, but hanging between the lines like smoke, is that an internal power source could explain both the blue emission and the sudden brightening that accompanied it. In other words, a technological artifact, something with an engine, with systems generating waste heat and emission profiles unlike anything seen in natural cometary physics, would look exactly like what we're observing. Now, before anyone dismisses this as science fiction disguised as data, consider what we know versus what we're merely assuming. We know that 3IATLAS exhibits 9 documented anomalies, 9 properties that are unusual, unexpected, or entirely unprecedented in the history of cometary observation. The list of anomalies is growing, and it's hard to ignore. The orbital alignment within 5 degrees of the ecliptic plane, the anti-tail, bizarrely pointing toward the sun, the extreme velocity, the massive nucleus, the early onset of outgassing, far beyond Jupiter's orbit, the nickel without iron signature, the carbon dioxide dominance, the fine-tuned trajectory, and now, the blue color. Individually, each of these could be dismissed. A statistical fluke, an unusual composition, a quirk of celestial mechanics. After all, nature is diverse, and the universe has a habit of surprising us. But 9 anomalies, 9 independent deviations from every model we have, all in one object? At some point, the cumulative improbability begins to weigh on the mind. At some point, you have to ask, are we witnessing the behavior of an extraordinarily strange comet, or are we observing something that isn't a comet at all? And there's one more coincidence, one that's impossible to ignore. The color change occurred precisely when 3IATLAS became unobservable from Earth. This isn't a conspiracy theory. It's geometry. As the object swung behind the sun, it entered solar conjunction, too close to the sun's glare for any ground-based telescope to track. For several critical days, 3IATLAS was hidden, invisible, its transformation unfolding beyond our sight. And during those crucial days, something extraordinary, or perhaps deeply ordinary, unfolded where no one could see. Exactly when 3IATLAS should have been at its most active, when solar heating ought to have driven torrents of outgassing, revealing the chemical heart of the object, it slipped behind the blinding veil of the sun for that short but critical window. It was beyond reach, hidden from every ground-based telescope on Earth. The only instruments still watching were the space-based solar observatories, their cameras not designed for comets. But by sheer coincidence, or something more, they were looking in the right direction. That timing has not gone unnoticed. Some have called it suspicious. An object whose trajectory threads between Mars, Venus, and Jupiter, then disappears at the precise moment we could have learned the most about it. It feels, they say, almost deliberate, as if the path were crafted to frustrate our instruments and conceal its nature. Others insist that's anthropocentric thinking. The universe does not plot or plan, and our bad vantage point is nothing more than cosmic coincidence. Both views are reasonable, both are impossible to prove nor disprove. But the timing, at the very least, is infuriating. Now, all eyes turn to mid-November. If predictions hold, 3IATLAS will re-emerge from behind the sun around the 11th, climbing into the pre-dawn sky, low in the constellation Virgo. What it looks like when it returns, whether dim and ordinary or stranger than ever, may decide which of these stories becomes truth. When 3IATLAS returns to the sky, it will first reveal itself to amateur astronomers, a faint, ghostly patch drifting slowly among the stars. Anyone with an 8-inch telescope or larger should be able to find it, a small blur of light whispering across the constellation Virgo. But if the unexpected brightening seen at perihelion continues, if this object keeps defying every prediction, then that faint patch may not stay faint for long. It could emerge significantly brighter than the magnitude 12 or 13 currently estimated, and more importantly, it will carry the next clue in its color. Will it remain blue, That strange sapphire hue that defied physics itself? Or will it fade back to red, or shift once more to the emerald green recorded in early September? Each outcome tells a different story about what 3IATLAS really is. A return to red would suggest the blue phase was temporary. A fleeting chemical reaction at perihelion, now burned away. A persistent blue would hint at something deeper, a sustained emission process, independent of the sun's warmth. And if it changes yet again, we may be witnessing a living chemistry, evolving as it sails farther from the solar furnace. But there is one scenario few have dared to speak aloud. What if it comes back dark? What if the brilliant surge we saw at perihelion was not the beginning of heightened activity, but the end? Comets can fragment, disintegrate silently under the sun's relentless heat. Sometimes they simply vanish, leaving nothing but a ghostly trail of dust and questions that never quite find answers. Comets are unpredictable creatures. They can erupt in sudden, spectacular outbursts, flinging vast clouds of dust and gas into space, and then fall eerily silent. Sometimes, under the crushing intensity of solar radiation, they simply cease to exist, disintegrating into invisible threads of vapor and ice. If 3IATLAS fails to reappear, if it emerges from behind the sun dim, or worse, not at all, the world of astronomy will ignite with speculation. Some will say it broke apart, that the immense tidal and thermal stresses of perihelion tore it to pieces. A simple, natural, if disappointing end. But others will remember the data. The non-gravitational acceleration that nudged its orbit. The subtle but measurable thrust that suggested something was actively altering its trajectory. And they will ask the question that most scientists are not yet ready to voice. Did it move? Did it change course? Did it do exactly what Dr. Lowe warned it might? Whatever the truth, the next critical moment arrives on December 19th, when 3IATLAS makes its closest approach to Earth, a mere 270 million kilometers away. Every major eye in the sky will be watching. Hubble, Webb, and a fleet of Earth-based observatories will turn their instruments toward this mysterious visitor, capturing spectra, colors, and light curves with a precision we've never had before. We will finally see its true color, its real spectrum, its chemical fingerprint. We'll know whether that impossible blue glow still lingers, and if it does, why. Until then, we are left suspended between observation and imagination, with an event that should not have happened, and explanations that no longer feel sufficient. We are left with a comet that glows bluer than the sun it orbits, a color that should not exist in such a world of ice and dust. And we are left to wonder, are we witnessing a fragment of exotic natural chemistry forged in some ancient alien star system, or are we seeing something else entirely? Something that perhaps wants us to wonder. Then came the numbers. Numbers that changed the tone of every conversation in every lab. They came from Dr. David Fennoia, a navigation engineer at NASA's Jet Propulsion Laboratory, whose career depends on the mathematical precision of plotting trajectories across millions of kilometers. When Fennoia publishes a report on non-gravitational acceleration, the community listens. When that report concerns 3IATLAS, it becomes impossible to ignore. October 31st, 2025. Fennoia's data described something unprecedented. An acceleration without a visible cause, a radial thrust of 135 kilometers per day squared, pushing outward from the sun. A transverse component of 60 kilometers per day squared, perpendicular to the solar direction. These are not rounding errors. They are not statistical ghosts hiding in the noise. These are real forces, large enough to alter an orbit, clear enough to defy every conventional model of cometary behavior. The question that follows is both simple and unbearable. What could be pushing it? This is thrust. Real, measurable, directional thrust, occurring precisely 1.36 astronomical units from the sun, at perihelion, at the moment of closest approach, when no telescope on Earth could see what was happening. Comets accelerate all the time. That must be stated clearly before speculation runs ahead of the data. Every active comet in the solar system experiences non-gravitational forces. As sunlight warms the nucleus, ice sublimates on the sunward side and gas jets erupt into space. The escaping vapor exerts a small but steady push, a natural rocket effect that has been understood for centuries. As Daryl Seligman of Michigan State emphasized in multiple interviews after the report went public, comets have non-gravitational accelerations all the time. It would be strange to find one that doesn't. And yet, What makes 3IATLAS different is not the fact that it accelerated. It's the scale, the timing, and the implications. The magnitude of the thrust compared to the negligible visible outgassing. The fact that it occurred exactly at perihelion, not gradually before or after, but in a sharp, mathematically precise burst of acceleration, right when it was hidden from view. And most troubling of all, what this thrust implies about mass loss. That's the calculation Evloeb performed. The one every researcher had quietly considered but few dared to publish. Because if his math is right, then what 3IATLAS did is not just statistically unusual, it is physically impossible for a comet. You want to produce 135 km per day squared of acceleration through the rocket, effect through normal gas ejection from a sublimating surface. You need to be losing mass, a lot of mass. Momentum has to be conserved. Every kilogram of gas that shoots away from the comet at a few hundred meters imparts an equal and opposite momentum to the nucleus. For an object the size and estimated mass of 3IATLAS, generating that much thrust means losing approximately 10% of its total mass over the span of a month. 10%. Think about what that means. This is not a gentle dusting of ice crystals evaporating into space. This is catastrophic mass loss. This is the comet essentially blowing itself apart, ejecting billions of tons of material in a continuous hurricane of outgassing that should create a massive, brilliant, unmistakable cloud of gas and dust around the nucleus. A cloud that should be visible across the solar system. A cloud that every telescope should easily detect when 3IATLAS emerges back into view. Lowe stated his prediction clearly. We should see a dense cloud of gas around it in November and December. Not might see, not could see, should see. Because if the non-gravitational acceleration is being caused by natural cometary outgassing, then the laws of physics demand that cloud exists. It is not optional. It is not uncertain. Momentum conservation is not a suggestion. It is a fundamental law that governs every interaction in the universe, from colliding galaxies down to billiard balls on a table. So what happens if we do not see that cloud? This is the question nobody in the mainstream astronomical community wants to ask out loud, but it hangs over every discussion of 3IATLAS like a storm front moving in. If December arrives, if Hubble and Webb and the ground-based arrays all turn their instruments toward this object at its closest approach to Earth, and if they see a relatively modest coma, a normal look tail, outgassing rates consistent with a typical comet at the distance from the Sun, then the rocket effect cannot explain the acceleration. The math does not work. The physics does not work. Something else must be producing that thrust. Lowe offered an alternative, not as his preferred explanation, not as what he thinks is most likely, but as a hypothesis that must be considered given the implications if it is correct. Then on gravitational acceleration might be the technological signature of an internal engine. Those are his words published in his analysis on October 31st, the same day Finocchia's report went public. An internal engine, a propulsion system, a device purpose-built to change velocity, to alter trajectory to maneuver. The immediate counter-argument is that one data point does not make a pattern. Non-gravitational acceleration has only been detected at perihelion. We do not have tracking data showing sustained thrust over days or weeks. We do not have evidence of course corrections or trajectory changes beyond what natural forces can explain. We have one measurement taken at one moment, during a phase, when we would expect maximum cometary activity. Anyway, building an extraordinary hypothesis on such limited evidence is premature, at best and irresponsible at worst. But there is the uncomfortable reality. We would not be able to detect sustained low-level thrust even if it was occurring. 3IATLAS is too far away, moving too fast, being tracked by too few observatories to measure subtle velocity changes in real time. The reason Finocchia could calculate the acceleration at all is because perihelion provides a known reference point. You can compare the predicted orbit calculated from gravitational forces alone to the observed position after perihelion and work backward to determine what additional forces must have acted. Outside of that window, the uncertainties are too large. The gaps in observation are too frequent. This is one of the most frustrating aspects of studying interstellar objects. They are here and gone. By the time we detect them, by the time we mobilize telescopes and coordinate observations and start gathering useful data, they're already well into their transit through the inner solar system. We get one chance, one pass. And if something happens during the weeks or days when we cannot observe them, when they are lost in the sun's glare or below the horizon or simply too faint to track, we miss it. We are left with gaps in the delta that speculation rushes to fill. The acceleration also occurred at the optimal moment for a maneuver. This is another detail that sounds conspiratorial until you understand the orbital mechanics. Perihelion is not just a point of closest approach. It is a moment of maximum opportunity. Every spacecraft engineer knows this. Every student of astrodynamics learns it early. When an object sweeps past the sun, its velocity reaches its orbital peak. At that instant, the sun's immense gravity acts as a natural amplifier. A brief pulse of thrust there, a fraction of what would be needed elsewhere, can alter a trajectory dramatically. It is the same principle used by NASA, ESA, and every mission planner who has ever sent a probe to the outer solar system on a budget of limited fuel and perfect timing. Fire your engines at perihelion, and the sun itself helps carry you farther, faster, with the least possible expenditure of energy. So if 3IATLAS were artificial, a probe, a vehicle, a piece of technology from another civilization, then perihelion is exactly when you would expect to see propulsion. You would wait until you were hidden from Earth's view, shielded by the sun's glare. You would wait until the gravitational assist was at its strongest. You would ignite your engines then. When fuel cost is lowest, trajectory change is greatest and no one is watching. Of course, the same logic applies in reverse. If 3IATLAS is entirely natural, then perihelion is still when its behavior would be at its most extreme. A comet pushed to its physical limits. Its ice is boiling off in torrents, its orbit subtly rewritten by the sun's relentless pull. In both cases, perihelion is where the truth hides. The question is whether that truth belongs to nature or to intention. If you're a natural comet, experiencing the full blast of solar heating, then perihelion is exactly when you would expect to see the maximum outgassing. And with it, the strongest rocket effect. In that sense, the timing proves nothing. It aligns perfectly with both explanations, the mundane and the extraordinary. We are left suspended in a state of uncomfortable ambiguity, knowing that something happened, but unable to say what or why. Then comes the question of direction. A 135 km/day acceleration, pushing radially outward from the sun, makes perfect sense for a classic rocket effect. Gas erupting from the sunward side would naturally push the comet away, exactly as physics dictates. But the second vector does not fit so neatly. A 60 km/day component transfers to the sun's direction, a sideways push. That is not what a simple symmetric outgassing event would produce. It suggests a lateral force, a motion that requires asymmetry, specific geometry, and persistent imbalance. To generate such a thrust, you would need jetting regions on the nucleus that are firing in preferred directions. Vents or fissures releasing gas with precise orientation, creating a net force perpendicular to the sun's pull. Again, this is not impossible. Comet nuclei are not smooth spheres of ice and dust. They are chaotic, fractured worlds, with cliffs, ridges, and pockets where volatile ices lie hidden beneath insulating layers. Sunlight strikes these irregular surfaces at uneven angles, heating some zones while leaving others untouched. A single bright patch of exposed ice can behave like a miniature thruster, producing subtle yet measurable changes in trajectory. And yet, to sustain a thrust that strong for that duration, and in that precise direction, requires an alignment so coincidental that even the most cautious scientists find themselves glancing twice at the data. Some regions on a comet's surface sublimate faster than others. The resulting gas jets erupt in whatever direction the local topography dictates. If a jet emerges along the evening terminator, that thin boundary between day and night on a rotating nucleus, it can indeed produce the kind of transverse acceleration we're observing in 3IATLAS. It's possible, but it requires the universe to cooperate in an almost theatrical way. The active regions must lie in just the right places. The axis of rotation must be oriented perfectly. The jets must have the precise balance of power and timing. One small change, one fissure opening slightly wider, one dust layer insulating a patch of ice, and the geometry collapses. The physics no longer works, and that's the maddening part. This configuration is possible for a natural comet, just barely. But a propulsion system, designed intentionally to alter velocity, would produce the same pattern by design. Thrust vectors that don't align with the sun's direction aren't an accident of topography. They're a choice. You point your engines where you need to go, not where the sunlight happens to be. It's a simple, elegant difference, and it's exactly what makes this so frustrating, because we have right now the technology to answer this. A close flyby mission, A probe with a suite of cameras, spectrometers, and particle analyzers could settle the question instantly. It could image the nucleus directly, observe the jets, measure their spectra, and tell us exactly what's being ejected and at what rates. In a single encounter, we could determine whether 3I-ATLAS is an unusually volatile comet or something else entirely. But missions like that take years to plan and launch. And by the time we're ready, 3I-ATLAS will be gone, leaving behind only its data and the growing suspicion that we may have just watched something we were never meant to understand. We could know within hours. A single flyby would tell us whether the acceleration matches the physics of natural outgassing or whether something else is happening. But there was no time. 3I-ATLAS was discovered on July 1st. Perihelion came on October 29th. 4 months, barely enough to write a mission brief, let alone design, build, test, and launch a spacecraft capable of an intercept. The proposals exist. The engineering studies are already done. Teams on both sides of the Atlantic have shown that future intercepts of interstellar objects are feasible and surprisingly affordable, but not this time. For 3I-ATLAS, we are prisoners of distance and timing. All we can do is watch from hundreds of millions of kilometers away and try to infer internal processes from the faint trickle of photons captured by telescopes. A few instruments still have a chance. The ESA's JUICE spacecraft will turn its sensors toward 3I-ATLAS between November 2nd and November 25th. It will see the comet in the aftermath of perihelion, when any lingering outgassing should still produce a vast, visible coma. But even that data must make its slow journey across the solar system. The results won't reach Earth until February 2026, months after the comet has vanished from sight, and perhaps long after we've already decided what we believe. The spacecraft is too far from Earth. The data rate is painfully slow. The queue of scientific observation stretches for weeks. So we wait, we speculate, we wonder, and in the meantime, 3I-ATLAS drifts on, unseen, unmonitored, doing whatever it is doing as it arcs away from the sun and back toward the darkness from which it came. If it is a comet, then it is shedding its mass, casting off ice and dust, building that expanding shroud of debris exactly as natural processes demand. But if it is something else, if those 9 anomalies are not coincidence, but signatures, then perhaps it is adjusting its course, changing its velocity, preparing for whatever comes next in a journey that began billions of years ago, in a star system we will never see. December 19th will decide which version of reality is closer to the truth. Until then, we are left with 135 kilometers per day squared of thrust, and no consensus on where it came from. The missing Mars images. October 2nd, 2025. On that date, 3I-ATLAS passed within 30 million kilometers of Mars. For comparison, that is closer than Mars has ever come to Earth in all of recorded history. Close enough that the spacecraft orbiting the red planet had their best opportunity yet to observe an interstellar visitor. A chance that humanity has waited a lifetime for and may never see again. And according to multiple sources, according to the geometry of the flyby and the capabilities of the instruments available, one particular camera had a perfect shot. HiRISE, the high-resolution imaging science experiment aboard NASA's Mars Reconnaissance Orbiter. A camera that can resolve features 30 centimeters across from an altitude of 300 kilometers above the Martian surface. A camera that has photographed avalanches mid-collapse, dust devils casting shadows, the parachutes and landing platforms of rovers that touched down decades ago. A camera that, when pointed at an object 30 million kilometers away, could achieve a pixel resolution of approximately 30 kilometers. That might not sound impressive until you remember that our best images of 3I-ATLAS from Hubble and KEK had resolutions 3 times worse. Those images were taken. Multiple researchers have confirmed that HiRISE was tasked with observing 3I-ATLAS during the Mars flyby window. The geometry was favorable. The pointing was possible. The observation was executed, and then the images disappeared into the bureaucratic void created by a government shutdown that began October 1st and lasted for weeks. A-Vibe has been explicit about this. In his appearance on the Joe Rogan Experience and his written statements in interviews with multiple news outlets, he has stated clearly that he requested access to those images. He reached out directly to the principal investigator of HiRISE. He received no response. He followed up. Still nothing. The images exist. They are sitting on a server somewhere in NASA's data pipeline. but they have not been released. They have not been made public. They have not been shared with the scientific community that desperately wants to see them. NASA has not confirmed the existence of these images. They have also not denied it. They have said nothing. The silence is deafening. Now, before this descends into conspiracy territory, we need to understand what actually happened during that shutdown. On October 1st, the United States government ran out of funding authorization. Various agencies, including NASA, were forced to furlough non-essential personnel. Scientific operations continued where possible, but communications shut down. Press releases stopped. Data sharing slowed to a crawl. The public F-facing infrastructure that normally makes NASA observations immediately available went dark. This was not unprecedented. Government shutdowns have happened before. They disrupt science every time. Observations get delayed. Data releases get postponed. The machinery of publicly funded research grinds to a halt. Not because anyone decided to hide anything, but because the people who process and release that data are sitting at home, unpaid, waiting for Congress to figure out a budget. It is bureaucracy, not conspiracy. It is institutional dysfunction, not deliberate obfuscation. But the timing is what NORSAT people, 3IATLAS, makes its closest approach to any planet during its entire transit through the solar system. The own moment when we could get high-resolution images from a vantage point we will never have again. And at that exact moment, the system for sharing those images shuts down. The coincidence feels almost deliberate, even though we know it is not. We know the shutdown had nothing to do with 3IATLAS. We know the budget impasse was about domestic policy and political maneuvering that had been building for months. But still, the timing. Lowe called it terrestrial stupidity. No evidence of aliens. Not a cover-up, but basic human incompetence getting in the way of discovery. The universe does not care about government shutdowns, he said. Science does not pause because politicians cannot agree on spending bills. And when you have a once-in-a-lifetime opportunity to observe an interstellar object at close range, losing that opportunity to bureaucratic paralysis is inexcusable. Florida Congresswoman Anna Paulina Luna apparently agrees. Reports indicate that she has been working tirelessly to secure the release of the high-resolution Mars images, leveraging every available channel to push NASA toward transparency. Whether this is genuine concern for science or opportunistic grandstanding is unclear. What matters is that someone with real authority is asking the questions astronomers have been asking since October. Where are the images? When will they be released? What exactly are they waiting for? Meanwhile, the European Space Agency did release its observations. Both Mars Express and ExoMars Trace Gas Orbiter, TGO, captured 3IATLAS during the October 1st to 7th window. The ExoMars TGO image shows the comet as a faint, fuzzy dot, barely distinguishable from the background stars. The spacecraft was tracking the fast-moving target, so the stars appear as streaks. While the comet remains stationary, it is an impressive demonstration of precision pointing and tracking, but it reveals almost nothing about the object itself. No resolved nucleus, no detailed coma structure, just confirmation that, yes, 3IATLAS was exactly where it was predicted to be. And yes, from 30 million kilometers away, it looks vaguely comet-like. NASA's Mars rovers and the Mars Reconnaissance Orbiter were also scheduled to observe the flyby. Ahead of time, NASA confirmed that Curiosity, Perseverance, and MRO would all attempt to capture images during the optimal window, and then the shutdown happened. The flow of information stopped. We do not know if Curiosity saw anything. We do not know if Perseverance pointed its cameras skyward. We do not know what MRO captured beyond the high-level observations that are said to exist, but remain unreleased. China's Tianwen-1 orbiter should have had a view as well, with over 14,000 published images of Mars and its surroundings. The Chinese space program is not shy about releasing spectacular data, yet there has been no statement from the China National Space Administration. No images, no press releases. No indication that they observed 3IATLAS at all. Some have suggested that this silence is more concerning than NASA's because it is voluntary, not the result of a shutdown. If the images had shown something ordinary, something consistent with a natural comet, why would China hesitate to publish them? Why pass up a chance to demonstrate observational prowess? The answer might be simpler: data processing delays. Space agencies routinely take weeks or months to calibrate and validate observations before they are released. Raw data from the spacecraft looks nothing like the polished images seen in press releases. Detectors have noise. Pixels must be corrected. Frames stacked. and every photon carefully accounted for. Even the most routine observations require time, patience, and precision, but in this case, that delay only amplifies the suspense. Cameras, of course, are not perfect witnesses. Their sensors collect more than light. Cosmic rays leave false streaks, and random electronic noise can masquerade as structure. Every frame must be checked, cleaned, calibrated, and compared. The absence of Chinese imagery, therefore, does not automatically imply secrecy. It may simply mean that engineers are being methodical, ensuring that what they release is scientifically unambiguous. But silence has gravity. In the absence of information, speculation rushes in to fill the void. Across Reddit threads, timelines are dissected frame by frame. YouTube analysts draw arrows between the government shutdown, the missing Mars data, and Lowe's warnings about 3IATLAS. TikTok explainers claim the object went dark, changed course, or is being hidden from public view by coordinated agencies. None of this is supported by evidence. All of it is unfalsifiable, because the data that could settle the debate remains out of reach. This is the paradox of doing science in the modern age, when the subject of study also becomes a cultural obsession. Transparency is expected, demanded, and when data does not appear on schedule, the public imagination fills in the blanks with cover-ups, conspiracies, and cosmic intrigue. Sometimes, those suspicions turn out to be justified. Far more often, they are phantoms of uncertainty. But without the images, without that single confirmation of what 3IATLAS looked like from Mars orbit on October 2nd, we are left adrift between reasonable skepticism and paranoid speculation, searching for truth in the silence between transmissions. What would those high-resolution images actually show us? If they exist, if they are ever released, what could we learn? The resolution would be enough to see the nucleus directly, measuring its size with precision, rather than relying on the broad estimates that currently place it anywhere from 440 meters to 5.6 kilometers. We could observe the coma structure, how gas and dust swirl around the nucleus, whether it is symmetric or shaped by jets and active regions. Color data could reveal the composition of the ejected material, allowing scientists to test hypotheses about volatile ices, carbon compounds, and more. Most importantly, we would see whether the object looks normal. Does it have the fuzzy, irregular, obviously icy appearance that every comet we've ever examined up close displays? Or does it show sharp edges, geometric features, surfaces that reflect light in ways ice and rock do not? Even at that distance, high-resolution imaging could not reveal microscopic detail, but it could make the critical distinction between a natural body and something artificial. It could provide a definitive answer to the question that Lowe keeps asking, and that most scientists have been hesitant to confront. The fact that we do not have those answers yet is maddening. The images may already exist, already captured and transmitted back to Earth, but remain inaccessible, locked away by political dysfunction, bureaucratic caution, or simple neglect. That is almost worse than if the observations had never been attempted at all. We were so close. 30 million kilometers is nothing on an astronomical scale. We had the tools, we had the opportunity, and we let it slip through our fingers. Lowe frames this as a failure of scientific culture, a cautionary tale about how bureaucracy and timing can snatch away answers that were, for a fleeting moment, within our grasp. We are too reactive, he argues, too willing to wait and see rather than preparing in advance. 3IATLAS was discovered in July. By late July, it was clear this object was coming close to Mars in October. There were months to coordinate observations to ensure every available instrument was pointed at the target to guarantee that data would flow smoothly, regardless of political circumstances. Instead, we relied on normal procedures, on the assumption that everything would work as it always does. And when it did not, we lost data we will never get back. The shutdown ended. NASA resumed operations. The data archive was quietly restored, but there has been no announcement about the high-rise images, no statement about when or if they will be released, no explanation for the communication gap. The episode has left a lingering distrust, a sense that even if nothing nefarious happened, the system is too fragile to handle the kind of rapid response that interstellar visitors demand. Meanwhile, 3IATLAS continues its journey, unaware and unconcerned with the political dramas and institutional failures that prevent us from studying it properly. By the time the images are released, if they ever are, the comet will be far from Mars, moving into a different phase of its solar transit. The moment will have passed, the opportunity will be gone, and we will be left wondering what we might have seen if we had simply been better organized, better prepared, more committed to the principle that scientific data belongs to everyone and should be shared, immediately, not hoarded behind bureaucratic walls. December will bring new opportunities. Hubble and Webb will observe from Earth orbit. Ground-based telescopes will track the object during its closest approach. We will get more data, better data, data that is not trapped in the maze of a government shutdown. But we will never get another Mars flyby. We will never get another chance at those 30-kilometer resolution images. Whatever they show, whatever they might have told us, that knowledge may be permanently out of reach. And that, more than any conspiracy theory or cover-up allegation, is the real tragedy of the missing Mars images. 9 anomalies and counting. When you study the universe professionally, you develop an instinct for what is normal and what is not. A comet with a slightly unusual orbit. Normal. A comet that outgasses earlier than expected. Unusual but not alarming. A comet that displays one genuinely puzzling characteristic, interesting enough for a research paper. But 9 separate properties that each individually strain the boundaries of what we've observed before. That is when pattern recognition starts, screaming that something fundamental is different about this object. Let us go through them systematically, not as a list of conspiracy fuel, but as an honest accounting of what makes 3IATLAS so persistently strange. Anomalyon, the orbital alignment. 3IATLAS travels along a trajectory that is inclined only 5 degrees from the ecliptic plane, the disk containing all the major planets. For an object arriving from interstellar space, from a random direction in the galaxy, this is statistically improbable. The calculation has been done by multiple independent researchers. The odds of an interstellar object naturally arriving with this alignment are approximately 1 in 522%. Not impossible, but not expected. Why does this matter? Because the ecliptic plane is where all the planets are. If you wanted to visit multiple worlds in one pass through a solar system, if you wanted to maximize your chances of close approaches to interesting targets, you would approach along the ecliptic. You would not come in at a steep angle that takes you fair above or below the planetary disk. 3IATLAS passes near Mars, will pass near Venus, will pass near Jupiter. Its trajectory gives it access to the inner solar system's most significant bodies. By coincidence or by design, 3IATLAS chose a path that was nearly optimal for observation. Anomaly 2, the anti-tail. Observed clearly in Hubble images from July and by ground-based telescopes through August, 3IATLAS displayed an extension of scattered light pointing toward the sun, not away from it. Comets normally have tails that trail away from the sun, pushed outward by radiation pressure and the solar wind. Anti-tails are not unheard of. They can occur when viewing geometry and particle dynamics create an optical illusion, making part of the debris trail appear sunward. But the persistence of the anti-tail in 3IATLAS, its prominence across multiple observations, suggests something more than a simple illusion. It hints at a physical process projecting material in an unusual direction. Lowe has proposed a provocative interpretation. The anti-tail could represent thrust exhaust, emissions from a propulsion system visible only from certain viewing angles. The mainstream explanation is more mundane. Large dust particles following divergent orbits from the nucleus create a fan of material that appears sunward from our perspective. Both interpretations fit the observations. Neither can be confirmed without closer direct observation. Anomaly 3. The velocity. 3IATLAS is moving faster than any interstellar object previously measured. At discovery, it traveled at approximately 61 km/s relative to the solar system's center of mass. For comparison, Oumuamua, 26 km, Lai Borisov, 32 km, 3IATLAS, nearly double the speed of the first interstellar visitor. This extraordinary velocity suggests a long and violent journey, accelerated by gravitational slingshots around multiple stars, gaining momentum over billions of years, and arriving in our solar system with a trajectory and speed that defy easy explanation. Or perhaps it suggests that 3IATLAS departed its home system with a high initial velocity, propelled by something beyond gravity alone. Higher velocity also means this object has likely visited more star systems, encountered a variety of stellar environments, and been bathed in cosmic radiation over the course of its journey. An object moving this fast is not on its first pass through a solar system. It is an ancient traveler, and its composition should bear the fingerprints of that long history. Whether it does, however, remains one of the questions scientists are racing to answer. Anomaly. 4. The massive nucleus. Current estimates place the diameter of 3IATLAS between 440 meters and 5.6 kilometers. The uncertainty is enormous, but even the lower bound makes it larger than Oumuamua by a significant margin. The upper bound would make it genuinely enormous, a mountain of ice and rock drifting through interstellar space. Large comets are rare, even in our solar system. Large interstellar comets should be extraordinarily rare, because ejecting massive objects from planetary systems requires extreme dynamical events. The odds of detecting such an object during its brief transit through our solar system are correspondingly tiny. Yet here it is. Lowe has pointed out that if the nucleus is on the larger end of the estimated range, 5 or 6 kilometers across, then it could not have originated from the typical reservoirs of interstellar ice. The mass density of large bodies between stars is simply too low. We would never expect to detect one in a human lifetime. For 3IATLAS to be this large and to be passing through our solar system now would require either astronomically improbable luck or a radically different origin story than the one we have been assuming. Anomaly. 5. Early outgassing. The comet became active far beyond Jupiter's orbit, at roughly 6.4 astronomical units from the Sun. Most solar system comets do not begin outgassing until well inside Jupiter's orbit, typically closer than 5 AU. The reason is straightforward thermodynamics. Ice must reach a threshold temperature before sublimating fast enough to produce a visible coma. Carbon dioxide ice, the dominant volatile in 3IATLAS, does sublimate more easily than water ice, which explains some early activity. But the intensity of the outgassing and the brightness achieved at such distances suggest a compositional structure unusually sensitive to weak solar heating. Anomaly. 6. The nickel without iron signature. This may be the most chemically bizarre property observed. Spectroscopic data from the KEK telescope and the Very Large Telescope clearly revealed strong emission lines from nickel atoms in the coma. Yet conspicuously, there were no corresponding iron lines. In natural astrophysical contexts, nickel and iron almost always appear together. They are synthesized in stellar cores and condensed together in planetary nebulae. Seeing one without the other is highly unusual, a chemical anomaly that does not fit conventional cometary models. Nickel and iron usually travel together through the interstellar medium. When you detect nickel, iron is almost always present except in 3IATLAS, and except in one very specific context, industrially manufactured nickel alloys. Specifically, alloys produced through the carbonyl process, where nickel tetracarbonyl is formed and then decomposed to yield pure nickel metal. This is a 19th century industrial technique developed for refining nickel on Earth. It is not a natural process. It does not occur spontaneously in space, yet somehow, 3IATLAS is emitting nickel in ratios to other elements that match industrial refining patterns, not natural cosmic chemistry. The standard rebuttal is simple. We just haven't detected the iron yet. The emission lines may be too faint or masked by overlapping spectral features. Future observations with better sensitivity could reveal iron in the expected proportions, and perhaps this anomaly would evaporate. But multiple independent observations have failed to detect iron. At some point, non-detection becomes a detection of absence. Anomaly. 7. Carbon dioxide dominance. A striking 87% of the observed volatile emissions are carbon dioxide. Only 9% are carbon monoxide, and a mere 4% is water. For a comet formed in the outer reaches of a typical planetary system, this ratio is completely inverted. Water ice is usually the most abundant volatile. Carbon dioxide is a minor component. 3IATLAS is defying conventional expectations, adding yet another puzzle to its growing list of anomalies. The fact that 3IATLAS is so heavily enriched in carbon dioxide points to a very cold formation environment, perhaps the outer regions of its home star system, where temperatures were low enough for carbon dioxide to remain frozen, while water ice had already been stripped away. Alternatively, it could indicate an ancient object, one that has been gradually losing its most volatile components over billions of years, leaving behind a comet enriched in the less volatile species that remain. This unusual composition also affects its behavior as it approaches the Sun. Carbon dioxide sublimation produces a cooling effect that suppresses water ice evaporation. This may explain why the rapid brightening at perihelion caught everyone by surprise. The carbon dioxide outgassing dominated until the comet approached the sun closely enough for water ice to finally sublimate in large quantities, triggering a burst of activity that models based on ordinary cometary compositions could not predict. Anomaly 8. The fine-tuned trajectory. This anomaly is less about a single measurement than a series of cumulative geometric coincidences. 3IATLAS arrives aligned with the ecliptic plane, passes within tens of millions of kilometers of Mars at a time when multiple spacecraft are orbiting the planet. Will pass near Venus in early November. Will pass near Jupiter in March. Reaches perihelion when it is hidden from Earth-based observers, visible only to space-based solar monitors. Individually, each of these facts is unremarkable. Taken together, they form a trajectory that seems optimized for planetary encounters while minimizing scrutiny from Earth, the most capable observation platform in the solar system.
We have to issue a warning.
Coincidence? Almost certainly. Yet the alignment of so many geometric factors in a single object is precisely the kind of scenario that makes low calculate. Probabilities and published papers urging that low probability explanations should not be dismissed when the consequences of being wrong are significant. Anomaly 9. The blue color shift at perihelion. We've discussed this before, but it belongs in this catalog because it is the most recent addition to the list, the most unexpected, the most resistant to explanation via conventional cometary chemistry, and the one that, if it persists when 3IATLAS re-emerges, could finally compel the mainstream scientific community to admit that this object is not just unusual, it is genuinely anomalous, demanding new physics or new chemistry to understand. 9 anomalies, 9 independent ways in which 3IATLAS defies the expected behavior of interstellar comets. Lowe assigned the object a score of 4 out of 10 on his scale of potential technological origin. 4 out of 10 is not certainty. It is not even a majority probability, but it is high enough to demand serious attention, high enough that dismissing the possibility outright would be scientifically negligent. The counter-argument, which most astronomers repeat when pressed, is simple. Space is diverse. Comets come in endless varieties and rare. Unexpected phenomena are always possible. Yet when you add together 9 independent anomalies, each pointing in a strange, unexpected direction, the result is more than a curiosity. It is a puzzle, an object whose history, composition, and behavior may be signaling something we have never seen before. Every object we observe closely reveals properties we did not expect. Oumuamua was bizarre. 2I Borisov was surprisingly normal, but still had its unique quirks. 3IATLAS? It is just another data point in the vast distribution of possible cometary properties.
Orbital parameters for the
If we observed 100 interstellar comets, we would likely see 100 different combinations of unusual features. The fact that 3IATLAS has 9 anomalies places it at the extreme tail of the distribution, not necessarily outside it entirely. This is a reasonable, conservative scientific position, the stance taken to avoid extraordinary claims based on limited data. But it comes with a heavy cost. It requires accepting a cascade of coincidences. It requires believing that 2% probabilities can happen. Industrial refining chemistry can emerge naturally in ways we've never observed. Trajectories can optimize themselves for planetary encounters purely by chance. Objects can turn color, accelerate, and brighten in ways that defy explanation, yet remain entirely natural, because the alternative is unthinkable. Maybe all of that is true. Maybe 3IATLAS is simply profoundly unlucky, a cosmic object at the extreme edge of probability, performing a sequence of highly improbable behaviors. Or maybe it isn't go simultaneously, or maybe the simplest explanation, the one that requires the fewest separate coincidences, is that this object is not like the others, that it is not a comet in the traditional sense, that it is something we have not encountered before and do not yet have the conceptual framework to understand. Either way, the list is not closed. If 3IATLAS continues to surprise us, if new observations in November and December reveal additional anomalies, the count will keep rising. And at some point, even the most conservative scientist will have to admit that calling something anomalous 9 times or 10 times or 11 times is just another way of saying we have no idea what we are looking at. The JUICE mission gamble. There is a spacecraft out there right now that has already seen what we're all waiting to discover. ESA's Jupiter Icy Moons explorer JUICE made its observations of 3IATLAS between November 2nd and November 25th, 2025. Multiple instruments, cameras, spectrometers, particle sensors. The spacecraft was perfectly positioned to observe the comet in the immediate aftermath of perihelion during the critical window, when any massive outgassing from that unexplained acceleration should still be visible, still creating a bright expanding cloud of debris that would be unmistakable in the data. JUICE saw it. Whatever is happening with 3IATLAS right now, whatever state it is in as it moves away from the sun, JUICE has already captured that information. The photons have already hit the detectors. The data has already been recorded. The observations are complete, and we will not know what they show until February 2026.3 months. 3 months of waiting while the most important data about 3IATLAS sits in a computer memory aboard a spacecraft that is too far from Earth to send that data home quickly. 3 months of speculation, debate, analysis of older observations, and growing frustration among astronomers who know that the answers they need are already collected, but utterly inaccessible. This is the reality of deep space missions. This is the price we pay for sending instruments to the outer solar system where communication is slow and bandwidth is precious. Let me explain why JUICE's observations matter so much, why they are potentially more valuable than anything Hubble or Webb or ground-based telescopes will collect in December. It is all about timing and vantage point. When 3IATLAS went behind the sun from Earth's perspective, it did not go behind the sun from JUICE's perspective. The spacecraft is on a completely different trajectory, currently performing gravitational assists as it makes its way toward the Jupiter system. From JUICE's location, 3IATLAS remained visible throughout perihelion. And more importantly, JUICE was looking at the comet during the days and weeks immediately after perihelion when solar heating was still intense, when any outgassing should have been at or near its maximum, when the acceleration detected by phenomena would have been creating observable effects. If Lowe's prediction is correct, if then-on gravitational acceleration requires 10% mass loss to be explained by natural rocket effects, then JUICE should have seen a massive coma, an enormous cloud of gas and dust, far larger and brighter than anything observed before perihelion. The particle sensors would have detected elevated densities of ions and neutrals. The spectrometers would have measured the composition and temperature of the outflowing material. The cameras would have imaged the coma structure, showing whether the emissions are symmetric or coming from active jets in specific parts of the nucleus. All of that data exists right now, stored in JUICE's memory, waiting to be transmitted. The reason for the delay is not mysterious or suspicious. It is purely technical. JUICE is currently about 2 astronomical units from Earth and moving farther away. At that distance, radio signals take approximately 16 minutes to travel one way. The spacecraft uses its main high-gain antenna as a heat shield during certain parts of its trajectory, which means it has to rely on the smaller medium-gain antenna for communications. The medium-gain antenna has a much lower data rate. Everything slows down. Science data gets prioritized and queued. Observations are transmitted in the order they were taken, with the most time-critical information sent first. The 3IATLAS observations, as scientifically interesting as they are not the primary mission objective. JUICE was designed to study Jupiter's icy moons, Europa, Ganymede, Callisto. That is where the major science return will come from, and that is what the mission operations team is focused on. The comet observations were a bonus, an opportunity target, something the spacecraft could look at, because it happened to be in the right place at the right time. But they are not driving the data transmission schedule, so we wait. We wait while JUICE continues its journey. We wait while the data slowly trickles back to Earth at kilobits per second. We wait while 3IATLAS grows dimmer and more distant. This is the gamble. This is the frustration of studying transient, unpredictable phenomena while relying on slow, distant communication systems. Every photon counts, every delay matters, and the universe does not wait for our schedules. We are forced to make decisions, plan observations, and even publish papers without access to data that already exists. Data that cannot be retrieved quickly enough to influence those decisions. It is like trying to solve a puzzle while someone holds back critical pieces, promising they will eventually be given. But not now. Not when they are actually needed. Some have suggested that ESA should prioritize the 3IATLAS data, moving its observations to the front of the transmission queue. But that is not how mission operations work. You cannot simply rewrite the entire data management plan because one target has become unexpectedly intriguing. There are contractual obligations to instrument teams, predetermined schedules for science objectives, and bandwidth allocations set years ago during mission planning. Altering all of that on the fly would create chaos, jeopardize other science, and require approvals from multiple levels of hierarchy. It is not going to happen. The data will arrive on schedule in February 2026. Until then, astronomers are effectively on their own. The situation is made even more complex by the fact that JUICE's observations might be the only reliable measurements of 3I/ATLAS in its immediate post-perihelion state. By the time the comet emerges back into view from Earth in mid-November, several weeks will have passed since perihelion. If the object underwent rapid changes at closest approach, if it brightened dramatically and then faded, or if it released a burst of gas that quickly dissipated, we will have missed it entirely. The only record of that critical transition will be in JUICE's data, and if that data contradicts what ground-based telescopes see in late November and December, if the comet appears different from what JUICE observed just weeks earlier, we will be left trying to explain not just one set of anomalies but two. The December 19th Earth approach will still be valuable. It will still provide high-resolution images, detailed spectra, precise photometry, but it will be observing a comet that has been away from perihelion for nearly 2 months. A comet that has cooled down, slowed its outgassing, potentially changed its appearance and behavior. We will be seeing 3I/ATLAS in a different state than JUICE saw it. Comparing the two datasets will require careful modeling, assumptions about how comets evolve as they move away from the sun, extrapolations that introduce uncertainty. If only we could see the JUICE data now. If only we could know what 3I/ATLAS looked like in early November. We could plan the December observation so much more effectively. We could target specific features, confirm or refute specific hypotheses, use our limited telescope time on questions that actually matter, rather than fishing blindly for answers. But we cannot, so wait. We speculate. We prepare for December without knowing what JUICE has already revealed. And we hope that when February finally arrives, when the data finally reaches Earth, it will have been worth the wait. That it will answer the questions we have been asking for months. That it will finally tell us whether 3I/ATLAS is an exceptionally strange comet or something else entirely. 3 months. It is not that long in the grand scheme of a multi-year space mission. But right now, with 3I/ATLAS dominating headlines and sparking debates, and keeping astronomers awake at night wondering what they are, looking at 3 months feels like forever. Low versus the world. The fight is not really about 3I/ATLAS. It is about how science should respond to anomalies, how much weight to give to improbable explanations, and whether the possibility of discovering something truly revolutionary justifies the reputational risk of being spectacularly wrong. Avi has made his position clear. When you encounter an object with 9 unexplained properties, when the cumulative probability of all those anomalies occurring naturally drops below a certain threshold, you have a scientific obligation to consider alternatives, even uncomfortable alternatives, even alternatives that sound like science fiction. The mainstream astronomical community disagrees loudly. Brian Cox, physicist and science communicator, stated it plainly. 3I/ATLAS is a comet made of carbon dioxide and water ices and bits of other stuff. It has a predictable orbit. It will pass the sun and continue drifting through the galaxy. The speculation about alien origins is, in his words, drill. It is sensationalism. It is misleading the public about how science works and what the evidence actually shows. Lowe's response was equally blunt. Cox is like a cave dweller who finds a phone and calls it just a rock. Real scientists play on the field guided by data, while commentators sit on the sidelines repeating popularity. The implication is clear. Cox is not doing science. He is performing for an audience. He is taking the safe position, the one that will not generate controversy or ridicule. Theory that allows him to maintain his status as a trusted voice of scientific authority. But safe positions do not lead to discoveries. They lead to confirmation of what we already believe. This divide, this fundamental disagreement about scientific methodology and risk tolerance, has become the subtext of every discussion about 3I/ATLAS. It is not really about whether the comet is natural or artificial. It is about whether we should even be asking that question out loud. Tom Statler from NASA represents the institutional position. It looks like a comet. It does comet things. It very strongly resembles the comet's Weckno. Yes, it has some properties that are unusual. Yes, it behaves slightly differently from solar system comets, but the evidence overwhelmingly points to a natural origin. To suggest otherwise based on the limited data we have is premature and irresponsible. It creates false uncertainty in the public mind. It damages the credibility of the scientific enterprise. Lowe has heard all of this before. He heard it when he suggested that One-Eye Oumuamua might be artificial. He heard it when he published his hypothesis about light sails in interstellar probes. He heard it when he founded the Galileo Projecto search for technological signatures and astronomical data. The criticism has been consistent. You're being too speculative. You're not being rigorous. You're chasing headlines instead of doing proper science. You're undermining public trust by entertaining ideas that have no solid evidentiary foundation. There is the problem with that criticism. Lowe is not ignoring the evidence. He is not making things up. He is looking at the same data as everyone else and arriving at a different conclusion about what deserves attention. He's assigning higher weight to the anomalies, lower weight to the standard explanations, and calculating that the probability space for exotic hypothesis is larger than most of his colleagues believe. That is not unscientific. That's a different approach to Bayesian reasoning about uncertain evidence. Consider the nickel without iron signature. The standard explanation is that iron is present, but we have not detected it yet. That future observations will find it. This is a reasonable hypothesis. It is conservative. It does not require new physics or new chemistry. But it is also unfalsifiable in the near term. You can keep saying we just have not looked hard enough every time a new observation fails to find iron. At what point do you accept that maybe, just maybe, the absence of iron is real and the chemistry of 3IATLAS is genuinely different from anything we have seen before? Lowe's answer is that we should be taking the observations at face value. If multiple independent spectrographs on multiple instruments have failed to detect iron, we should consider the possibility that there is no iron to detect. And if there is no iron, if nickel is being emitted without its usual companion element, then we need an explanation for why. The carbonyl refining process is one explanation. It happens to be an industrial process, one associated with technological manufacturing. That does not mean 3IATLAS is artificial, but it does mean we should not dismiss the possibility without further investigation. The scientific establishment has reflexive immune response to suggestions of alien technology. This is understandable. The field has been burned before by wild speculation that turned out to be wrong. Pulsars were once briefly thought to be artificial beacons, before we understood neutron stars. Fast radio bursts generated similar speculation about advanced civilizations before natural mechanisms were identified. The WOW signal, the face on Mars, the canals of Venus. Every time an extraordinary explanation proved false, every time natural phenomena were misinterpreted as something more. This history creates a cognitive bias. When someone like Lowe suggests that an interstellar object might be artificial, the immediate reaction is often not to evaluate the claim on its merits, but to pattern match it to previous false alarms. It sounds like the face on Mars all over again. It sounds like someone desperate for attention, making claims they cannot back up. It sounds like bad science. But pattern matching can also be wrong. Just because previous claims of alien technology were incorrect does not mean all such claims are incorrect. The universe is under no obligation to follow our expectations. Somewhere in the vast catalog of astronomical phenomena, there may exist actual evidence of technology created by non-human intelligence. And if that evidence does exist, it will initially appear anomalous. It will violate expectations. It will seem too unlikely to be true. Scientists who point it out will be criticized and ridiculed, accused of sensationalism and poor judgment, until enough data accumulates that the conclusion becomes unavoidable. Lowe argues that we are in that initial phase with 3IATLAS, where the anomalies are significant enough to warrant serious investigation. Assigning a 30–40% probability to a non-natural origin, he contends, is not wild speculation. It is a reasonable assessment given the available evidence. If we dismiss this possibility now, if we close off that line of inquiry simply because it makes us uncomfortable, we might be repeating the mistakes of past scientists who dismissed continental drift, rejected the existence of meteorites, or insisted that the universe was static and eternal. His critics respond firmly. Extraordinary claims require extraordinary evidence, they say, and the evidence that 3IATLAS is anything other than a comet is not extraordinary. It is suggestive at best. They argue that the anomalies can all be explained through conventional physics. The fact that these explanations require several unlikely conditions to occur simultaneously does not justify abandoning natural explanations in favor of unproven alternatives. Darrell Seligman of Michigan State University exemplifies this camp. He has studied 3IATLAS extensively, publishing papers on its composition and trajectory. and he remains confident that it is a comet. In his view, the non-gravitational acceleration is normal for comets. The unusual nickel emission does not require exotic chemistry to explain. The orbital alignment is unlikely, but not impossible. Its high velocity is extreme, but still within the expected range for objects ejected from nearby star systems billions of years ago. Every anomaly, when examined individually, has a plausible natural explanation. Lowe's response is precise. This misses the point. It is not about whether each anomaly can be explained individually. It is about whether the collection of anomalies taken together is more easily explained by one hypothesis versus another. The question is cumulative, not piecemeal, and that, he argues, is where the potential for a non-natural origin becomes scientifically credible. In Lowe's judgment, an artificial object would naturally display exactly the suite of properties we see in 3IATLAS. It would be aligned with the ecliptic to access multiple planets. Its chemistry would be unusual because it is made of manufactured materials, not natural ices. It would show non-gravitational acceleration if it had propulsion systems. It would be large and fast if designed for interstellar travel. It might turn colors if internal systems were generating heat or emissions. None of this is proof. Lowe acknowledges that repeatedly, but he argues that proof is not the standard we should be applying at this stage. The standard is whether the hypothesis is worth investigating, whether it deserves resources, attention, and follow-up observations. And his answer is emphatically yes, because the consequences of being right are so enormous, even a 10% probability, or 5%, justifies the effort required to find out. The counter-argument is equally compelling. Chasing low-probability hypotheses is a waste of limited resources. Telescope time is precious. Funding is scarce. Diverting attention to unlikely explanations risks missing opportunities to study things we know are real and important. It also risks training the public to expect aliens around every corner, creating a boy who cried wolf scenario where genuine discoveries are met with skepticism because the field has been saturated with false positives. This is the impasse. Both sides have valid points. Both sides argue from defensible positions within the framework of scientific methodology. Both are frustrated because the disagreement is not really about data. It is about values, about what kind of risks are worth taking, about whether it is worse to miss a genuine discovery because of conservatism or to waste resources on speculation because of credulity. 3IATLAS has become the battleground for this larger conflict. Every new observation, every anomaly, every unexplained brightening or color change is interpreted through these opposing frameworks, each side seeing the object not just as a comet or perhaps a probe, but as a reflection of how science chooses to balance risk, curiosity, and caution. Lowe sees evidence accumulating in favor of his hypothesis. His critics see confirmation that they were right to be skeptical, that the object is revealing itself to be natural after all, just unusually natural. December will not resolve this debate. No matter what the observations show, both sides will interpret the data in line with their priors. If the comet displays that predicted massive gas cloud, Lowe's critics will say, it is natural outgassing, exactly as we said. If the comet does not display that cloud, Lowe will say, the rocket effect cannot explain the acceleration. Something else is happening. The evidence will not be definitive because it never is. There will always be room for alternative interpretations, additional hypotheses, and wait and see. The only thing that could truly settle the question is close-up observation. A spacecraft mission to 3IATLAS. Cameras capable of resolving surface features. Instruments that can sample the coma directly. Perhaps even a lander that could touch the surface and determine its composition and structure with absolute certainty. But that mission does not exist. It cannot be launched in time. 3IATLAS will leave the solar system before we could reach it. So the debate continues. Lowe versus the world, and everyone else watching, waiting to see who history will judge to have been right. The brightening that broke the models. Qichang Zhang from Lowell Observatory and Carl Battams from the U.S. Naval Research Laboratory have been tracking comets for years. They understand how comets brighten as they approach the sun. They know the equations, the physics, the empirical relationships that connect heliocentric distance to apparent magnitude. When a comet gets closer to the sun, it heats up. Ice sublimates faster. More gas and dust gets released. The coma grows larger and brighter. It is predictable. It follows power laws. You can calculate what the brightness should be at any given distance if you know a few basic parameters about the comet's composition and size. 3IATLAS did not follow those serials. Between September and October 2025, as it plunged toward perihelion, it brightened at a rate that far exceeded every prediction. Not by a small margin, not by the kind of variation you expect from comets that are slightly more active or slightly less dusty than average, by a factor that required adding extra terms to the equations, by an amount that suggested something fundamentally different was happening inside or around this object. The numbers tell the story. During the early part of its approach, 3IATLAS was brightening roughly as expected, following a power law where brightness increased proportionally to distance from the sun rays to some negative exponent. Typical comets show exponents around -3 or -4. As you get twice as close to the sun, you get somewhere between 8 and 16 times brighter. 3IATLAS was following something like that pattern through July and August. Observers could predict its magnitude a few weeks in advance with reasonable accuracy. Then in September, something changed. The brightening accelerated. The data started deviating from the model predictions. And by early October, when space-based solar observatories could track the comet as it moved behind the sun, from Earth's perspective, the brightening had become extreme. Zhang and Badams calculated that 3IATLAS was following a power law with an exponent of approximately 7.5 plus or minus 1. That is nearly double the rate of normal comets. It is brightening so rapidly that every day closer to the sun results in a dramatic increase in apparent magnitude. Why does this matter? Because brightness is not just about aesthetics. Brightness is a proxy for activity. When a comet gets brighter, it means more surface area is actively sublimating. More ice is turning to gas. More dust is being lifted off the nucleus. The total energy budget of the system is increasing, and that energy has to come from somewhere. For a normal comet, it comes from solar heating. Sunlight hits the surface, warms the ice, drives sublimation. The rate at which this happens depends on how much sunlight is being absorbed, which depends on distance from the sun. Twice as close means 4 times more solar energy per unit area. 4 times more energy means faster sublimation, but not 7.5 power law faster. Something else must be contributing. One possibility is that the comet underwent a compositional transition. Early in its approach, when it was farther from the sun, carbon dioxide ice was the dominant volatile. Carbon dioxide sublimates easily even at low temperatures, which explains why 3IATLAS started out gassing beyond Jupiter's orbit. But carbon dioxide also has a cooling effect. As it evaporates, it absorbs heat from the surrounding material, lowering the surface temperature and suppressing the sublimation of other ices, particularly water. The hypothesis is that as 3IATLAS got closer to the sun, the carbon dioxide layers exhausted themselves or retreated beneath the surface, exposing water ice that had been protected until that moment. Water ice sublimates much more vigorously once it reaches the right temperature. The latent heat of sublimation is different. The vapor pressure curves are different. You can get a sudden burst of activity when water ice becomes the dominant volatile. A transition that would not show up gradually in the data, but rather as a sharp increase in brightening rate right around perihelion. This is a reasonable explanation. It fits the chemistry we know 3IATLAS has. It does not require new physics, but it also requires very specific conditions. The carbon dioxide layer needs to be thick enough to suppress water sublimation for months, but thin enough to erode away at just the right moment to create the observed brightening surge. The nucleus needs to have a layered structure with carbon dioxide on top and water underneath, which is the opposite of what you would expect if the comet formed in a cold environment where carbon dioxide should freeze first, and water should be deeper in the interior. The alternative explanation, the one that Zhang and Badams carefully avoided stating explicitly, but which hangs in the air whenever this data is discussed, is that the brightening is not entirely due to sublimation, that some additional energy source is contributing, that something inside 3IATLAS is generating heat or releasing stored energy in a way that adds to the solar heating and creates a brightening curve that natural processes alone cannot reproduce. Law predictably has run with this idea. He pointed out that the blue color observed at perihelion is consistent with emission from a source hotter than you would expect from passive solar heating. If 3IATLAS has an internal power source, if it is generating energy through some mechanism other than absorbing sunlight, that energy has to go somewhere. It would heat the surface, it would drive additional sublimation, it would make the comet brighter than predictions based on solar heating alone, and it would create spectral signatures, emission lines, colors that do not match what you get from reflected sunlight passing through a cloud of dust and gas. The mainstream response is that this is unnecessary speculation, that invoking an internal power source to explain the brightening requires assuming the existence of something for which we have no independent evidence. The compositional transition hypothesis, while requiring very specific conditions, is still vastly more probable than the idea that 3I-ATLAS contains an energy source of unknown origin. Occam's razor is invoked. We should prefer the simpler explanation, and the simpler explanation is that this is a comet with an unusual but natural composition, behaving in an unusual but natural way. But Occam's razor is only useful if simplicity is defined correctly. Is it simpler to assume a very specific layered structure with precise compositional boundaries that happens to produce a brightening surge exactly at the moment the comet is unobservable from Earth? Or is it simpler to assume that an object already exhibiting 9 other anomalies has a 10th anomaly that is mechanistically related to the first 9? The answer depends on what you already believe about 3I-ATLAS. If you are convinced it is a natural comet, any natural explanation, no matter how contrived, is simpler than an artificial one. If you are open to the possibility that it is something else, adding one more piece of evidence to that hypothesis may be the simpler path. What makes the brightening especially puzzling is that we do not have a complete light curve. Observations before perihelion show the acceleration of brightening. Space-based observations right at perihelion show that the comet was extremely bright, bluer than the sun, and emitting strongly in wavelengths suggestive of gas rather than dust. But we lack continuous observations showing whether the brightening peaked and then declined, whether it plateaued, or whether it continued increasing even after perihelion, when one would expect it to start fading. This gap in the data is maddening. If we could see the post-perihelion light curve, if we knew how quickly 3I-ATLAS faded, or whether it faded at all, we could constrain models significantly. A rapid decline would suggest a temporary outburst, perhaps a large fragment of the nucleus, breaking off and exposing a surge of ice that quickly exhausted itself. A plateau would indicate sustained high activity, which is harder to reconcile with passive solar heating, unless the nucleus is larger than current estimates suggest. A continued increase would be nearly impossible to explain naturally, and would strongly support the idea that something beyond solar distance is controlling the brightness. JUICE may have captured this data. The spacecraft observed the comet during the critical window and could have measured its brightness daily, tracking the evolution of the light curve through perihelion and into the post-perihelion phase. But we will not see that data until February. For now, we are left guessing, building models on incomplete information and hoping that when the full picture emerges, it clarifies what we are seeing now. Amateur astronomers have attempted to fill the gap. Ahadi Boone, a skilled comet hunter, spotted 3I-ATLAS in GOES 19 images on October 18th and tracked it until October 24th. His observations suggested the comet remained bright, comparable to nearby magnitude 11 stars, even as it moved away from perihelion, hinting at sustained activity rather than a brief outburst. However, these observations are limited. The GOES solar monitoring camera was not designed for precision photometry of faint comets. The error bars are large and calibration is uncertain. It is better than nothing, but not definitive. Ground-based observations will resume in mid-November, when 3I-ATLAS emerges from behind the sun. Dozens of telescopes will measure its brightness, track changes over the following weeks, and compare the results to pre-perihelion data, finally beginning to fill in the missing pieces of this puzzle. If the comet remains significantly brighter than it was in September, maintaining high activity even as it moves farther from the sun and cools, that will be a major clue about what happened at perihelion. If it is faded back to expected levels, following a normal power law decline, that will suggest the brightening was temporary, a phase transition or compositional quirk that has now passed. But there is a third possibility that few dare consider openly. What if 3I-ATLAS does not brighten according to any power law, normal or anomalous? What if its brightness varies in ways that do not correlate with solar distance at all? What if we see flares, sudden increases followed by declines, patterns that suggest internal processes rather than external heating? That would be the strongest evidence yet that something deeply unusual is happening. Even skeptics would be forced to acknowledge that 3I-ATLAS is not behaving like any comet we have ever studied. The brightening that broke the models is not just a curiosity. It is a window into the internal workings of 3IATLAS. Every photon that reaches our telescopes carries information about its origin, the processes that generated it, and the activity on or inside the comet. When those photons arrive in quantities that violate expectations, forming a light curve that does not fit the equations, they are telling us our understanding is incomplete. Either the comet's composition is stranger than we imagined, its structure more complex than assumed, or something else is providing energy beyond what the sun delivers. December will give us more photons, more data points, a better light curve, and eventually we will understand why 3IATLAS brightened the way it did. We will build a model that fits the observations. We will publish papers explaining the physics and chemistry. But whether that explanation involves natural processes or something more exotic remains to be seen. For now, we have a comet that defied predictions, broke the models, and left us wondering what else it might do before it leaves the solar system forever. What the color changes really mean: red in July, green in September, blue in October. 3 different colors across 4 months, each representing a fundamentally different state of matter and energy in the coma of 3IATLAS. This is not normal. This is not how comets typically behave. Yes, comets can change color as they approach the sun, as different ices sublimate at different temperatures as the balance between dust and gas shifts. But the progression we're seeing, the specific sequence of red to green to blue, tells a chemical story that does not quite make sense when you try to write it down. Let us start with red. When 3IATLAS was first observed in detail in July, when Hubble captured its image showing the peculiar antitail, the color signature was reddish. Dust dominated sunlight, reflecting off small particles, carbon ryegrains, organics that had been baked by cosmic radiation during billions of years of interstellar travel. This is what you expect from a comet that is still relatively cold, still far enough from the sun that sublimation is just beginning. That the coma is mostly comprised of solid particles, rather thangas. Red means dust. Red means passive reflection of sunlight. Red means business as usual. Then came the green phase. September 7th, during that total lunar eclipse, astrophotographers Michael Jagger and Gerald Riemann captured images from Namibia that showed 3IATLAS glowing with a distinct green hue. Blue-green specifically, with the comet displaying a coma 2.5 arc-minutes across, clearly visible in both blue and green filters. This is classic comet behavior. Green means diatomic carbon C2 molecules fluorescing under solar ultraviolet radiation. It is the signature of organic compounds. Breaking down of complex carbon chains being shattered by sunlight and emitting that characteristic emerald glow as electrons cascade back to their ground state. Except there is a problem. Earlier spectroscopic observations from the Very Large Telescope and from Keck showed that 3IATLAS has unusually low levels of carbon chain molecules. The paper by Luis Salazar Manzano explicitly noted that 3IATLAS is among the most carbon chain depleted comets known. The ratio of cyanogen to C2 is extremely high, meaning there is very little of the molecule that normally produces green emission. So where was the green color coming from? One possibility is that the spectroscopic observations were incomplete. That C2 was present, but at levels too low to detect with the integration times and sensitivities available. Then as the comet got closer to the sun, as sublimation accelerated, enough C2 accumulated in the coma to produce visible green fluorescence. The molecule was always there, just hiding below the detection threshold until conditions became favorable. Another possibility is that the green was not from C2 at all. Other molecules can produce green emission under specific conditions. Certain nickel compounds, when excited by ultraviolet light, can fuse at wavelengths that appear greenish. Given that 3IATLAS is emitting nickel in unusual quantities, given that the nickel lacks its usual iron companion, maybe the green phase was not about carbon chemistry, but about metal chemistry. Maybe we were seeing the signature of nickel tetracarbon, L breaking down, releasing nickel atoms, that then absorbed and remitted light in the green part of the spectrum. This is speculative. No one has measured nickel fluorescence from a comet before. Because no comet has displayed prominent nickel emission before, we are in uncharted territory trying to explain observations that do not fit existing frameworks. Viewed, if the green phase was related to nickel rather than carbon, that would connect it to the broader pattern of chemical anomalies. It would be one more piece of evidence that 3IATLAS has a composition unlike anything else we have studied. And then it turned blue. Not just slightly blue, not blue-tinged intensely, remarkably blue, bluer than the sun. And this is where conventional explanations start to break down entirely. Blue emission from a comet is rare but not unheard of. Ionized carbon monoxide can fluoresce in blue wavelengths when hit by solar wind particles, and ultraviolet radiation. The ion tail of a comet, the part that points directly away from the sun driven by magnetic fields rather than radiation pressure, often has a blue color because it is made of ionized molecules rather than neutral gas or dust. So seeing some blue in the spectrum of 3IATLAS would not be surprising. But this was not some blue. This was dominant blue. The color observations from stereo, from GOES 19 all showed that the coma was emitting more strongly in blue wavelength than infrared. For an object that should be cooler than the sun. For an object that should have dust reening its reflected light. For an object that should be producing emission primarily from molecules with characteristic wavelengths in the ultraviolet, visible green or near-infrared blue dominance is wrong. It suggests a thermal spectrum that is hotter than expected. Or it suggests emission from a source that preferentially produces blue light through some process that is not simple fluorescence. The thermal interpretation runs into immediate problems. For 3IATLAS to have a thermal spectrum that peaks in the blue, it would need a surface or coma temperature of several thousand Kelvin that is hotter than most stars. Hotter than any natural object in the solar system except the sun itself. You cannot heat ice to several thousand Kelvin with sunlight from 1.36 AU away. You cannot even heat rock to those temperatures at that distance. If the blue color is thermal, blackbody radiation from a hot surface, then the heat must be coming from inside the object, not from solar heating alone. This brings us back to the question of internal energy sources. What could generate enough heat inside a comet to produce visible blue emission? Natural radioactive decay is far too weak. Even an implausibly high concentration of uranium or thorium would generate negligible heat compared to what is required. Chemical reactions, the kind that could occur if pockets of volatile compounds suddenly mixed and reacted, could produce bursts of heat, but sustaining that heat long enough to dominate the emission spectrum, and in a way that produces blue dominance rather than a broad thermal profile, requires extremely specific and seemingly contrived conditions. The alternative, one Lowe has been hinting at without stating outright, is that the blue emission is not thermal at all. It might be line emission from an unknown molecule or process, a signature of energy release through a mechanism we do not yet understand. What kind of chemistry or physics could create such emission without producing corresponding features elsewhere in the spectrum is unclear. Perhaps it is not natural at all. If 3IATLAS has internal systems, generating power and radiating waste heat, the color of that radiation would depend on the temperature and the materials involved. Certain industrial processes, types of lighting, or plasma states produce characteristically blue emission. In that case, the color we see could be the signature of technology, not nature. A spacecraft running on a nuclear reactor would have a thermal spectrum set by the reactor's operating temperature. A probe using ion engines would produce a blue glow from ionized propellant. These are engineering phenomena, not astronomical ones. But if you are observing an engineered object rather than a natural body, engineering phenomena are exactly what you would expect. This makes the color progression particularly intriguing. Red to green to blue is not what you would expect from simple solar heating. A comet warming as it approached the sun should shift from red toward yellow, maybe eventually white, as the thermal spectrum moves to shorter wavelengths. You would not expect discrete phases dominated by different emission mechanisms at different times. Such a sequence suggests evolving chemistry, changing composition, or different processes activating as conditions shift. A layered nucleus could explain this. Early on, dust dominates because only the surface is active. Later, as the dust erodes, carbon-rich ices beneath start sublimating, producing green emission. Even later, at closest approach, water ice deep in the interior finally sublimates, and the coma becomes dominated by water vapor and its dissociation products, some of which might emit blue under intense solar UV. This narrative is plausible. It requires the nucleus to have a very particular structure, but it is not physically impossible. What we need to resolve this question is spectroscopy. Good spectroscopy. High-resolution spectra that can identify individual molecular emission lines, that can measure ratios and temperatures and velocities. The color observations tell us that something unusual is happening. They do not tell us what. To answer that, we need to decompose the light into its constituent wavelengths, see which molecules are present and how abundant they are. Map the chemistry of the coma in detail. December's observations will include extensive spectroscopic campaigns. Hubble, Webb, the Gemini telescopes, KK, the Very Large Telescope. All have spectrographs, all will be pointed at 3IATLAS during its closest approach. The data they collect will either confirm that the blue color is from known molecular emission, In which case we update our models and move on, or it will show something unexpected, some spectral signature that does not match any molecule in our databases. And if that happens, if we see emission lines that we cannot identify, then the speculation will intensify because we will have direct evidence that 3IATLAS is made of something or doing something that we've never encountered before. The color changes are not just pretty pictures. They are data. They encode information about temperature, composition, energy flow, physical state. When we see a comet change from red to green to blue across a few months, we're watching a transformation, a progression through different regimes of physics and chemistry. Understanding that transformation, mapping it to known processes or identifying where it deviates from known processes is one of the key challenges of studying 3IATLAS. And if the color remains blue when the comet emerges in November, if weeks after perihelion it is still glowing with that strange azure light, that will be evidence of sustained emission from a source that does not depend on solar distance. That will be evidence that whatever created the blue color at perihelion is still active, still releasing energy, still making this object unlike anything else in our catalog of comets. Red to green to blue. 3 colors, 3 states. 3 pieces of a puzzle that we're only beginning to assemble. December 19th, the moment of truth circle. This date on whatever calendar you use to track cosmic events. December 19th, 2025. The day when 3IATLAS makes its closest approach to Earth, passing within 270 million kilometers of our planet. 8 astronomical units. Close enough that every major telescope on and above Earth can observe it simultaneously. Close enough that we will finally get the high-resolution data, the detailed spectra, the precision photometry that will either confirm this object is an unusually interesting comet or reveal it to be something else entirely. Lobers framed this date as the ultimate test of his predictions. If then-ungravitational acceleration detected at perihelion was caused by natural outgassing by the rocket effect of sublimating ice, then we should see a massive cloud of gas around 3IATLAS in December. Not a subtle enhancement, but a marginally larger coma than expected. A dense, bright, unmistakable envelope of gas that can only have been created by losing 10% of the comet's total mass over the span of a month. The laws of momentum conservation demand this cloud exists if the natural explanation is correct. If the cloud is not there, if 3IATLAS appears in December with a modest coma without gassing rates, consistent with a typical comet at that distance, then the rocket effect cannot explain the acceleration. Something else must have produced that thrust, and the list of alternatives is short and uncomfortable. Either the mass estimates are wrong by an order of magnitude, meaning the comet is vastly more massive than we think, and therefore does not need as much gas ejection to produce the observed acceleration. Or the acceleration was not caused by gas ejection at all. The mass estimates come from brightness measurements and assumptions about albedo. If 3IATLAS is much darker than we assume, if it reflects very little sunlight, and most of its brightness comes from the coma rather than the nucleus, then the nucleus itself could be much larger. A larger nucleus means more mass, which means less mass loss required to produce a given acceleration. This is plausible. We have never resolved the nucleus directly. All our size estimates are indirect based on how bright the object appears and how we interpret that brightness. We could be wrong, but being wrong about the mass by the factor needed to make the numbers work would require the nucleus to be implausibly large and implausibly dark. It would require 3IATLAS to be the largest interstellar object ever detected by a huge margin, and to have a surface that reflects almost no light at all, which contradicts the spectroscopic evidence showing that the surface is ejecting dust and ice. There is a limit to how much you can adjust parameters before the explanation becomes more unlikely than the phenomenon it is trying to explain. So December 19th becomes a fork in the road. One path leads to a natural comet with an unusual, but ultimately explicable set of properties. The other path leads to a genuine anomaly that demands new thinking, new hypotheses, maybe even acknowledgement that we are looking at something that does not fit into our existing categories of astronomical objects. The observation campaign is already being planned. Hubble Space Telescope will use its wide-field camera to image the comet in multiple filters, measuring colors and coma structure with the resolution that only space-based imaging can provide. James Webb will point its near-infrared spectrograph at the target, obtaining spectra across wavelengths that are blocked by Earth's atmosphere, identifying molecules that are invisible to ground-based telescopes. Webb's infrared sensitivity will also allow it to measure the temperature distribution in the coma, seeing whether there are hotspots, regions where heating is stronger than simple solar radiation can explain. On the ground, the Gemini telescopes in Hawaii and Chile will conduct coordinated observations, using their adaptive optic systems to achieve near diffraction-limited imaging in the near infrared. The Very Large Telescope in Chile will deploy its full arsenal, multiple spectrographs operating simultaneously to cover ultraviolet, visible, and infrared wavelengths. Keck Observatory will use its cosmic web imager to map the three-dimensional structure of the coma, seeing how gas and dust are distributed in space rather than just projected onto the plane of the sky. Dozens of smaller telescopes will participate. University observatories, amateur astronomers with equipment sophisticated enough to contribute useful photometry, automated survey telescopes that can take frequent measurements, tracking how the brightness changes hour by hour. The International Asteroid Warning Network, which added 3IATLAS to its observation campaign as a training exercise, will coordinate tracking across multiple sites to ensure continuous coverage. This is unprecedented. Never before have so many resources been devoted to observing a single comet. 1 was gone before we could mobilize this kind of campaign. 2I Boris got significant attention, but not at this scale. 3IATLAS has captured the imagination of the astronomical community in a way that previous interstellar visitors did not. Partly because of its anomalies, partly because of the Loeb controversy, partly because it will be observable 4 months, giving us time to plan and coordinate and execute a comprehensive study. The data from December will answer several critical questions. First, what does the nucleus actually look like? Can we resolve it? Can we measure its size directly instead of inferring it from brightness? Hubble has the resolution to potentially see the nucleus as an extended object rather than a point source, especially if the coma is not too bright. If we can measure the nucleus size, we immediately constrain the mass, which tells us how much gas ejection is required to produce the observed acceleration. Second, what is the coma density? How much gas and dust is present around the nucleus? This is measurable through multiple techniques. Direct imaging and scattered light shows dust spectroscopy is the key. It reveals gas through emission lines, whose intensity depends on the number of molecules present. Comparing these lines to the continuum gives the gas-to-dust ratio, a fundamental property that tells us about the comet's composition and activity. If 3IATLAS has a huge, diffuse coma, that would support the massive outgassing hypothesis. If the coma is modest, comparable to other comets, it would contradict it. Spectroscopy also tells us what molecules are present and in what ratios. Emission lines can be measured and compared to laboratory data and theoretical models. We will learn whether carbon chains are abundant enough to explain the green color, whether the blue emission comes from carbon monoxide ions or some unknown source, and whether unexpected chemical species hint at unusual formation conditions or internal chemistry. Finally, spectroscopy can reveal structure in the coma: jets, streamers, shells, or asymmetries. Active comets often display jets of gas erupting from specific regions, patterns that reveal the rotation of the nucleus and the distribution of active areas. If 3IATLAS shows strong asymmetric jets, the non-gravitational acceleration could be explained naturally as a result of uneven outgassing. If the coma is symmetric, with no clear jets, explaining the non-gravitational acceleration through standard comet physics becomes much harder. And fifth, what about the color? Will 3IATLAS still appear blue in December, or will it have faded back to red, green, or white? The evolution of color is one of the most diagnostic indicators of energy sources. If the blue was temporary, driven by specific perihelion conditions that no longer apply, it was likely a natural but unusual phase transition. If the blue persists, even at 1.8 AU from the Sun, it points to an ongoing emission process that demands explanation. Timing is crucial. December 19th marks the closest approach, but the comet will be observable throughout December and into January. It will rise before dawn, visible for several hours in the morning sky before twilight intervenes. Fortunately, the new moon occurs in mid-December, offering dark skies right when observations are most critical. Later in December, lunar interference returns, but the comet's brightness and altitude will largely mitigate its effects. Multiple observations over several weeks are essential. A rapid decline in brightness would suggest that the perihelion outburst was temporary, and the comet is returning to baseline activity. A slow decline, or sustained brightness, would indicate prolonged activity, whether from continued sublimation or from some internal process, independent of solar heating. Time series data is always more informative than single snapshots. Tracking the comet over days and weeks reveals dynamics, trends, and evolution that point toward the underlying mechanisms, and inevitably, leaves room for surprises. 3IATLAS has already surprised us multiple times. It surprised us with its early outgassing. It surprised us with its nickel mission. It surprised us with its rapid brightening. It surprised us with its blue color. Every time we think we have figured it out, every time we build a model that explains the existing data, new observations come in that do not quite fit. December might bring more surprises. The coma might have features nobody predicted. The spectrum might show emission lines from molecules nobody expected. The nucleus might look different from what models suggested. Loha said that if the massive gas cloud is not present, if his prediction is falsified, it would be evidence that the rocket effect is not responsible for the acceleration and something else must be invoked. But he is also hedged, noting that mass estimates are uncertain, that the required gas cloud might be fainter than expected. That absence of evidence is not always evidence of absence. This is good scientific practice. Predictions should be testable but not so rigid that a single observation can definitively prove or disprove them. Reality is always more complex than our models. Interpretation is always required. Theme and stream scientists who disagree with Low are equally invested in December's observations. They expect to see a comet, an active, outgassing, sublimating comet with a composition that is unusual but comprehensible. They expect the spectrum to show the molecules we have already detected, plus maybe a few more. They expect the brightness and color to be consistent with natural processes, perhaps with some refinement to the models, but nothing revolutionary. They expect 3IATLAS to fit into the box we have built for interstellar comets, even if it sits in a corner of that box where nothing else currently resides. Both sides will get data. Both sides will analyze it. Both sides will publish papers. And both sides will argue about the interpretation because that is how science works. Consensus emerges slowly when the phenomena are ambiguous. But December will at least narrow the possibilities. It will give us facts where we currently have speculation. It will replace models with measurements. And that movement from uncertainty toward knowledge, however incremental, however incomplete, is what makes the observation campaign worth the effort. 1 month, one closest approach, one chance to see 3IATLAS from the best vantage point we will ever have. And then it will move on, receding into the darkness, leaving us to make sense of what we saw. A message from a dead world physicist. Brian Cox called it exactly that, a message from a dead world. Not in the sense of alien communication or technological artifacts, but in the deeper, more poignant sense that 3IATLAS is a fragment of something that no longer exists. The star system where it formed, the planetary disk where it accreted from ice and dust and organic molecules, the gravitational dynamics that eventually ejected it into interstellar space. All of that happened billions of years ago. The world that created 3IATLAS is gone, changed beyond recognition. Perhaps the star has evolved off the main sequence. Perhaps the planets have migrated or been destroyed. Perhaps nothing remains of the original system except this one icy traveler drifting through the galaxy, carrying the chemical signature of a place and time we will never see. That perspective is humbling regardless of whether 3IATLAS is a comet or something more. It is a reminder that we live in a universe where most of what exists is inaccessible to us, where most of history has already happened and left only faint traces, where the objects we study are often the last survivors of processes that ran their course aeons ago. 3IATLAS has been traveling for somewhere between 3 billion and 11 billion years. It has witnessed the evolution of the galaxy in ways we cannot imagine. It has passed through regions of space we will never reach, and now by pure chance its trajectory happened to intersect ours for a few months. If it is a natural comet, if all the anomalies resolve into unusual but comprehensible physics and chemistry, then 3IATLAS is still teaching us something profound. It is showing us that comets from other star systems can be radically different from comets in our own, that the formation conditions around other stars, the chemical compositions of other planetary disks, the processes that shape and age interstellar ice over billions of years, all create diversity we have barely begun to explore. Every interstellar object is a data point about the galaxy as a whole. Every observation of these rare visitors expands our understanding of what is possible, what is common, what is strange in the cosmos beyond our immediate neighborhood. The age estimates are particularly striking. 7.5 billion years old. That is older than your solar system by more than 50%. Thesan did not exist when 3IATLAS formed. Earth did not exist. Life did not exist. The galaxy looked different with more young stars, more active star formation, a different distribution of metals and heavy elements. Whatever star system created 3IATLAS was part of an earlier generation, formed from material that had been through fewer cycles of stellar birth and death. The chemistry should reflect that. The isotope ratios should be different. The trace element abundances should tell asteroid about nucleosynthesis processes that occurred billions of years before our own solar system began. This is why spectroscopy matters so much. We are not just measuring what molecules are present right now as the comet sublimits. We are measuring what elements were available in that ancient star system, what conditions existed in its outer reaches where volatiles could condense, what kind of radiation and cosmic ray environment the nucleus experienced during its journey through interstellar space. Every emission line, every isotope ratio, every molecular abundance is a clue about the history encoded in this object. If the carbon dioxide dominance is real, if 3IATLAS truly is 87% carbon dioxide biomass, that tells us something about temperature and pressure in the disk where it formed. Carbon dioxide preferentially condenses in very cold environments, colder than the regions where most solar system comets formed. This suggests 3IATLAS originated far from its parent star, perhaps in the equivalent of our Oort Cloud or beyond. It was born in the deep cold and has remained cold ever since, never approaching close enough to a star to lose its volatile ices until now. The nickel without iron signature, if it persists in December observations, points to chemistry. We do not fully understand natural astrophysical processes, always produce nickel and iron together, because they are synthesized together in supernova. They are both iron group-elements with similar properties. They condense together in stellar outflows. They should be inseparable. Yet 3IATLAS is emitting nickel prominently while iron remains undetected. This could mean the formation environment had unusual conditions chemistry that preferentially incorporated nickel over iron. Or it could mean the nucleus has been processed somehow, altered by some mechanism that segregated the two elements. Or it could mean we're seeing an industrial signature, the result of refining processes that do not occur naturally. That last possibility is what keeps low in the conversation. It is what prevents mainstream astronomers from completely dismissing his arguments, because even if the probability is low, even if every instinct says this must be natural, the nickel signature is genuinely hard to explain. And when you couple it with the other 8 anomalies, when you look at the full suite of properties rather than any single one in isolation, the cumulative improbability starts to weigh on you. It starts to feel like something needs to give, like our models need to stretch further than they comfortably can, like we are being forced to accept too many coincidences. The trajectory through the solar system is one more piece of this puzzle. 3IATLAS will pass near Venus in early November 2025. It already passed near Mars in October. It will pass near Jupiter in March 2026. Its path takes it through the plane where all the interesting objects are, where all the potential targets for observation or interaction reside. If you were designing a mission to survey a star system, if you wanted to visit multiple planets in one pass, this is the trajectory you would choose. You would align with the ecliptic. You would time your perihelion to coincide with favorable planetary positions. You would maximize the science return from your flyby. Of course, natural objects can also follow such trajectories. Comets from the cloud occasionally come in one ecliptic-aligned orbits purely by chance. The probability is low, but not zero. And we've observed enough comets over the centuries that eventually the unlikely ones appear. 3IATLAS might just be one of those unlikely cases. A natural object that happens to have a trajectory that looks optimized because the geometry happened to work out that way. But it is worth asking what we would see if an interstellar probe did visit our solar system. What signatures would betray its artificial nature? What observations would distinguish it from a natural comet? Lowe has argued that most of the anomalies of 3IATLAS are exactly what you would expect from a technological object. The orbital alignment, the unusual composition, the acceleration without visible outgassing, the size and speed, the fine-tuned trajectory. If all of those properties appeared in a human-made spacecraft, we would instantly recognize it as artificial. We give it a pass as natural only because we assume the alternative is too improbable to consider seriously. That assumption might be wrong. We have no idea how common technological civilizations are in the galaxy. We have no idea how many might have built interstellar probes. We have no idea what fraction of those probes might pass through our solar system in any given century. The numbers could be zero. They could be small. They could, in a sufficiently old and densely populated galaxy, be large enough that encountering one in a human lifetime is not absurd. We do not know. And in the absence of knowledge, we default to skepticism, to the assumption that the universe is mostly natural and technology is rare. But that assumption is just an assumption. It is not based on evidence. It is based on what feels reasonable given our limited experience. 3IATLAS is testing those prior. It is asking whether we are willing to update our beliefs when confronted with anomalies, whether we are open to possibilities that seem unlikely but cannot be definitively ruled out, whether we can hold multiple hypotheses in mind simultaneously without prematurely collapsing to the one that feels most comfortable. The observations in December will help. They will provide data that constrains the possibilities that make some explanations more plausible and others less, but they will not provide certainty. They will not definitively prove 3IATLAS is natural or artificial. They will move the needle, shift the probabilities, give us more information to work with. And that is all science can really do when dealing with unique, ambiguous phenomena that do not fit neatly into existing frameworks. In March 2026, 3IATLAS will pass near Jupiter. The Juno spacecraft in orbit around the gas giant might be able to observe the comet from yet another vantage point. Europa Clipper, if it has arrived in the Jupiter system by then, could add its instruments to the campaign. These observations will be the last good look we get before 3IATLAS leaves the solar system entirely, heading back out into the interstellar medium from which it came, and then it will be gone. Another object in the catalog, another paper in the journals, another debate that never quite resolved itself because the evidence was insufficient and the phenomenon too fleeting. Unless something dramatic happens, unless the December observations reveal something so anomalous, so clearly outside the bounds of natural behavior that even the skeptics have to acknowledge we are looking at something extraordinary. That is the hope and the fear. The hope that we might witness something genuinely unprecedented, something that expands our understanding of what exists in the universe. The fear that we might discover we are not alone, that other intelligences are out there, and that we've been too blind or too cautious to recognize the signs when they appeared in our telescopes. Either way, 3IATLAS has already succeeded in making us question our assumptions. It has forced conversations that would not otherwise have happened. It has pushed scientists to articulate why they believe what they believe, to defend their positions with evidence rather than authority, to engage with uncomfortable ideas rather than dismissing them out of hand. And it has reminded us that the universe is full of mysteries, that we have explored only a tiny fraction of what exists, that every new object, every strange observation, every anomaly that defies easy explanation is an opportunity to learn something we did not know before. Whether 3IATLAS is a comet from a dead world or something more, it is teaching us and we should be grateful for. The lesson, however, it ultimately resolves. The ancient ice remembers it, carries information about a time and place we cannot visit, about chemistry and physics, and perhaps about the ambitions of beings we've never met. All we can do is look, measure, analyze, and try to understand the message encoded in those frozen molecules. Racing through the darkness at 61 kilometers, a message from a dead world, or a messenger from a living one. December will bring us closer to knowing